And hello, hope everyone's doing well. So, nope, I did that last time, didn't I? I hope you all are doing all right. Today we are going to take a look at three more rules or theorems related to circles. In particular, these have to do with the lengths of line segments. So up until now, we've been dealing with angles and arcs. Now we're going to be dealing with lengths of line segments caused by chords, secants, and tangents. So let's get started right on the first one. This video is going to be a little bit long because of the way I want to do it. I want to give you the rule, but then I also want to provide a proof for each. So let's get started here and say we've got circle O. Now let's say in circle O, whoops, you've got two chords, which I'll draw in here and here. And let's just label these. Let's say this is chord AB and chord CD, and those two chords intersect at some point E. You're going to see this one a lot. The rule you have whenever two chords intersect in a circle, the product of the parts are equal. In other words, all we have here is that AE, this section here, times the other part of that same chord. AE times BE has to equal DE times CE. Oops, wrong letter. DE times CE. So in other words, if this was 1, and oh, that's bad, I shouldn't have labeled that one 1. If I had that this was 6, and this one here was 4, then I could say that this here is 3 and this is 8, and we can see 6 times 4 gives me 24. 3 times 8 gives me 24 as well. That's always going to be the case when two chords intersect. Multiply the two parts of one of those chords times the two parts of the other chord, the parts being what are defined by that little intersection point. So that is the rule. Now let's prove it. Again, any rule, any theorem in mathematics can be proved. If someone tells you that there is no proof, they're wrong. If it's a theorem, if it's true, it can be proven. If it can't be proven, it's not true. That's why math is so great. So I'm going to do a simple two-column proof here. Here's my statement, here's my reason, and go down. Okay, so first off, I want to state with what I've been given. I'm going to say in circle O, chords AB and CD intersect at E. And of course that was given. Okay, now we're going to get to the part that is not as obvious as far as what you would have to do. So the first thing is, if you remember back to when we did our other proofs, I said whenever we have this product thing going on, really what that is hiding underneath, remember this is what we need to prove, what that really is hiding underneath is that is the result of cross multiplication. In other words, I can take this, I can do a little bit of algebra to rearrange this to have that AE over DE would be equal to, so AE over DE would be equal to CE over BE. If this is what I want to get to, that's a proportion. Remember, whenever we wanted to prove proportions, the best way to do that would be to find two similar triangles. So that's my motivation for the next step here. What I'm going to do is I am going to draw in this line and this line. So I'm going to say, draw AD and BC. And my reason whenever I do something like that is by construction or just construction. going to help me later. Okay, so first thing, I've got two triangles here. I want to show that those two triangles are similar. First thing I'm going to do is I'm going to go ahead and just make it a little easier on myself. I'm going to call that angle 1. I'm going to call that angle 2. Angle 1 is congruent to angle 2 because they're vertical angles. Vertical angles are congruent. Okay, that's one pair of angles right off the bat. Now the next thing to do here is I have an inscribed angle here that I'm going to call angle 3. And then I've got an inscribed angle here that I'm going to call angle 4. If you notice, this inscribed angle is subtending arc AC. This inscribed angle is also subtending arc AC. So I'm going to set in the groundwork to first say that arc AC is equal to itself. That's the reflexive property. Now that I've said that, I'm going to say that angle 3 is equal to 1/2 of arc AC. And the same way I could say that, I can also say that angle 4 is 1/2 of arc AC. My reason there being that inscribed angles that subtend the same arc, or excuse me, I'm a step ahead of myself. I can say that inscribed angles are half the measure of the arc they subtend. Now that I've got that statement and reason in there, I can now say that angle 3 is equal to angle 4, or I could say they're congruent, would probably be more appropriate. And now that's just a simple substitution. Because I know AC is equal to itself, so if I have half of AC on both sides, I can say that 3 and 4 are equal to one another. Now that I have, in these two triangles, I had this pair of angles that were congruent, and now I've also got this pair of angles that are congruent, I can say that triangle ADE is similar to triangle CBE by angle-angle. The most common way we always show that two triangles are similar. Since I know those two triangles are similar, I'm going to continue my proof right up here. I can say that AE over, so this part over DE is equal to, I'm going to take a corresponding side in the other one, CE over BE. My reason for that is that similar triangles are in proportion. And now that I've got that done, I can cross multiply here. AE times BE is equal to CE times DE. My reason is that the product of the means is equal to the product of the extremes, or cross multiplication. And with that, we've proved it. So you know that for a fact. You can always take that and always use it from here on out. There's your proof. Now we're going to deal with the next rule, which is a little bit more complicated. So I'm going to clear that out, and I'm going to go ahead and draw myself a new circle. Now, this rule has to do with when you have two secants that cross outside of the circle. So I'm going to go ahead and draw my secants. Here is one of them. Here's the other one. And again, I will place my center here. Now with this diagram and with all these diagrams, you're doing this all without a loss of generality, meaning it doesn't matter if you have this exact diagram. It's more the fact that you have the two secants or the two chords or whatever it is. That's why we start off with that given statement. It's telling you what you're starting off with can lead to the rest, and it doesn't matter exactly how they're lined up. So Here are my two secants, and I'm going to go ahead and draw and label these as A, B, C, D, and E. Now, the rule when two secants meet at an external point is a little bit more complicated. I'm going to write it out first. The rule is that if you take AC times BC, it's equal to EC times DC. So realize what's going on there. It is this whole secant times its external part is equal to this whole secant times its external part. None of those parts are equal to one another. This whole secant AC, you can tell, is not equal to EC. Same way DC and BC are not equal. The place people mess up in this one is they will accidentally say that AB times BC is ED times DC. The two parts multiplying each other is what happens when you have chords, the two things inside the circle, like that last problem. In this one, it is the whole secant times just part of it is equal to the other whole secant times just part of it. And those parts have to be the exterior ones. So in this problem, if I just come up with a quick example off the top of my head, like a genius, which I am, I'm going to say if this part here was, I'm just going to use the same numbers as before. This part here was 6, and this part here was 4. Wait, no, 6. Okay, then this part here could be, oh man. So what do I have here? I have this whole entire one is 10 times the external part would be 4, which is 40. So I'm trying to think of numbers in my head that are going to give me 40. I could do 10 and 4. I could also do 8 and 5. So I would have to have that this entire thing here added up to 8 by saying this is 5 and this is 3. So then I would have 5 plus 3 is 8 times 5 would give me 40. So let's just make sure I did that right. AC in this case would be 10. And then I would have times its external part, which is 4. Now EC would be 3 plus 5, which is 8, times my external part here, which is 5. 40 indeed equals 40. So is this drawn to scale? No. I just wanted to give an example to show you how you would actually put this problem into play. Like, for example, they may have given you this and said, find DC, in which case you'd set it up the same way, except you would say, I would have here, AB and BC. For EC, I would have to call this X. And then I'd have to say, I have 3 plus X times X. So then I would have 3X plus X squared is equal to 40. So then I'd have X squared plus 3X minus 40 equals 0, and then go through and try to solve it that way. So then in this case, I would have X plus 8 and X minus 5. So then I could have that X plus 8 equals 0, or X minus 5 equals 0, which would give me that X equals negative 8. I'm going to reject that root because I can't have a negative length of a line segment. And the one that I would accept is that X would equal 5. So there's that whole rule and the way you would apply it going into place. Now let's prove it. So again, I'm going to start off by drawing that circle. And I'm going to draw in my line segments, or my secants in particular. So there's one of them. There's a second one. Here is my center. Oop, that's not quite the center. Maybe somewhere around there is a little bit closer. I don't actually need the center for this problem. I just always like drawing it in if I've got a circle. And I'm going to label it in the same way. A is here, B is here, C is that external point, D is here, E is here. So again, I'm going to start off my statement reason table by filling in my givens. And the givens in this case, what do I have? I have circle O with secants A, B, C, and EDC intersecting at C. Given. This proof is a little bit more complicated. It requires a little bit of trickery. So, what is it I'm trying to prove? The thing I want to get to is I want to be able to say that AC times BC is equal to EC times DC. Again, whenever you have something like that, a string of two products multiplied equals two products multiplied, you're going to want to look for similar triangles, just like we did before. Now, in this case, it's hard to see where those triangles are. In reality, if you look, AC is this big line over here. EC is this big line over here. Now, if you look, I could draw in this line segment here, and those would be two sides of this big triangle. The other two parts I have are BC and DC. And it might be clear to you that I could then draw in this line segment to have this small triangle here. So that's going to be what I'm going to do for my next step. I'm going to say that I need to draw AE and BD. And my reason there is by construction again. It's saying do this because it's going to allow me to prove stuff. By construction. Okay? I've got those in there. There's one angle that both of these triangles share, which is over here. Now I could use three-letter names, ACE, BCD, but it's unambiguous. If I just say C is congruent to C, by reflexive, there's only one angle C I can be talking about here. Now's the hard part, having to get those other angles. The reason this one's so complicated is because I kind of need a lemma. I need something I can use as a stepping stone in this proof. In particular, what I want to do is I want to say that this angle here, which I'm going to label as angle 1, I want to be able to say angle 1 is congruent to angle 2, just like that, because those are two angles in those two triangles. In order to do that, I'm going to need to use this angle here, which I'm going to label as angle 3. Now here's where that lemma comes in. If you look, angles 1 and 3 are not equal, right? This one's acute, that one's obtuse. They are definitely not congruent angles, but they are both inscribed angles. And if I look at what angle 1 traces out, angle 1 subtends arc AD, or ABD, I should say, whereas angle 3 subtends arc AED. So they are subtending opposite arcs in this case. Now think about what that means. I know that angle 1 is half the measure of arc ABD. Likewise, I know that angle 3 is half the measure of arc AED. And that's the same reason I used before. Inscribed angles are half the measure of their subtended arcs. If you notice, arcs A, B, D, and arcs AED start and end at the same spot, which means that together they would make up a circle. ABD plus AED, and I'm talking about arcs here, equal 360 degrees. Because opposite arcs, that's a phrase, opposite arcs form a circle. Opposite arcs means angles that form a circle. So by definition, that's what they do. So ABD and AED, I could say are opposite arcs by definition, but I'm just going to leave it in here. So ABD and AED add up to 360 degrees. That's good. So then if I have half of each of them, 1/2 of ABD plus 1/2 of AED would have to equal half of 360. In other words, 1/2 of arc ABD plus 1/2 of arc AED would have to equal 180 degrees. All I've done there is just a little bit of multiplication. I'm now going to substitute. Angle 1 plus angle 3 is equal to 180 degrees. I've substituted in angle 1 for half of ABD. I've substituted in angle 3 for 1/2 of AED. What I was saying I wanted to use as a lemma before. This entire section right here, I could replace with a single statement that I could have proved. I could have said that angle 1 plus angle 3 equal 180 degrees because inscribed angles that subtend opposite arcs are supplementary. Instead, I've just gone through and I've derived that proof in the middle of my other proof. So I now know that angle 1 plus angle 3 equal 180 degrees. Cool. How is that going to help me? Well, if you notice, angle 2 and 3 form a line here, which would mean that angle 2 plus angle 3 also equal 180 degrees because they form a linear pair. Linear pairs are supplementary. Would you agree that I could subtract angle 3 from both sides and saying that angle 1 is equal to 180 minus angle 3? And similarly, I could say that angle 2 is equal to 180 minus angle 3. Sure. So, angle 1 is congruent to angle 2 by substitution. So I now know that this angle here is congruent to this angle here. That's enough for me to say that those two triangles I drew are similar. I'm going to try to keep continuing the proof right over here, but I may run out of room. Statement and a reason. So now I can say that triangle, my big one, I'm going to say AEC, is similar to, what's my other one? Well, my other one would be DBC. My reason is angle. Whenever I do triangles are similar, 9 times out of 10, we try going for angle, just because it's easier. It's easier to show two angles are congruent than 2 pairs of sides are in proportion and also a pair of angles. That would be using side angle side for triangles. So now that I've got those two, or now that I've got that statement in there and I know these two triangles are similar, heavy lifting's done. I can say that these two are in proportion, aren't they? So if I take the whole side of this big triangle and this big one, if I say that the ratio of AE, this triangle's big side, over, well, what's this triangle's big side? would be DC. That is going to equal, I'm going to take this triangle, the side that goes between the two angles I labeled, EC, over, and now this one that goes between the two is BC. Similar triangles have proportionate sides. Now let's cross multiply. Oh, did I mean AE when I wrote AE before? No, I meant AC. Oop, that's a mistake. Let's change that now. Yeah, AC. This triangle's big side over the small triangle's big side is equal to EC being the big triangle's intermediate side over the other ones. So now I'm going to cross multiply. AC times BC is equal to EC times DC. And that's what I wanted to prove. So I'm done with that one. Like I said, these are intense proofs. They're a little bit crazy. But I wanted to give you the proofs to show you that these things are always true. Now, there are two other theorems we need to know in here that are really similar. The proofs for them are a lot more simple. So I'm going to recap what we know. So again, if you have a circle and I've got two chords that intersect, I'm going to label these with lowercase letters, A and B, C and D. I know that AB, A times B, is equal to C times D. When you have two intersecting chords, the parts of those two chords multiplied in one is equal to the product of the other two parts of the other chord. That's the first thing we know. The next thing we know is what we just proved in the last one. Oops, not what I wanted. If I have two secants that meet at an external point, and let's say I go and I say, okay, this is this entire, actually no, let's do it a little different. Just so you can, why are you not letting me erase? Sometimes I get mixed up between using my pen and using my mouse, so forgive me. Let's just go by the parts of it. Let's say X is the length from here to here, because this is often the way these problems are going to be given to you. And Y is the external part of this tangent. W will be the internal part. I said tangent, I meant secant. W will be the interior part of this secant. Z will be the exterior of this one. The theorem tells me, and this is where you have to be careful, people will accidentally mix up the two of these. It is not true that X times Y is equal to W times Z. That is a false statement. However, it is true to say that this entire secant, which would be X plus Y, if I multiply that times the external part of that secant, it is equal to the entire other secant, W plus Z, times the external part Z. That is the second theorem I have, and we just proved that. So, the reason I said there are two other ones that are a little less substantial. This is one that I like to call the bird theorem. I'm drawing two tangents here. The reason I call it the bird theorem is it kind of looks like a bird's head and its beak. And that's actually what goes through with the theorem of this one. I have one tangent here, and I have another tangent here. Let's say this one has a length of X. The length being from the point of tangency to that point of intersection, and this point of tangency to this point of intersection. This one's also x. Proof for it's actually pretty simple. Let's call this tangent AB. I'm not actually going to write the proof of this one. I'm just going to talk through it. This one is CB, and this is circle O. I can draw in AO and AC. I know those two are congruent because they are radii. I can then go through and draw in this line OB, which I know is congruent between the two of them because it is reflexive in that case. So I've got these two triangles here, and in this case, whenever you have a radius drawn to a tangent, it's 90 degrees there. Same thing over here. So I've got two right triangles. By hypotenuse leg, the two triangles are congruent. So by CPCTC, these two legs are congruent. So anytime you have that circle with two tangents drawn to an exterior point, so you've got your circle, and I say, oh, here is one tangent. Here's the other tangent. Just remember Lacella's bird theorem. It looks like a bird. Those two parts are congruent. Done. The two parts, again, being from the point of tangency over to here. It's not saying the tangent being this whole line segment is equal to this whole line segment. No, because I can arbitrarily extend or shorten either of these. So that's that one. The very last one is a hybrid of these two. What happens if I have a circle? Oops. If I have a circle, and I've gone and drawn a secant and a tangent. I'm not going to walk through the proof of this one because this proof is very similar to the last one. I'm just going to, or not the last one, but it's very similar to the secant one. Here's my center O. If I call this secant ABC, and this is tangent DC. AC times BC, so this whole secant times the exterior part. Imagine if they were both secants. We know the rule is the entire secant times the exterior part is equal to the entire secant times the exterior part. So the entire secant times the exterior part is equal to this entire segment, DC, times its exterior part. AC times BC is just equal to DC squared. So when you have a secant and a tangent meeting at an exterior point, the entire secant times its exterior part is equal to that tangent squared. So again, let's come up with an example here. Let me say that this is 2. And then this is 5. No. We'll say this is 3. So then, this entire secant here is 5. And I want to know what's the length of DC. Well, according to this rule, I have to take the entire secant times its exterior part, and that's going to give me the tangent squared. So, oops, I got ahead of myself. 5 times the exterior part is just 2. 5 times 2 is 10 is equal to x squared. That tangent would be equal to the square root of 10. And you can kind of reason that in your head by drawing in this guy here. You know that's a right angle. You've got hypotenuse, that's 5. Then you can work through it using the Pythagorean theorem. So those are those 4. Really, it's only 2 with a special case theorems we need to know about line segments. Let me know if you have any questions. Thanks for watching it. See you guys soon. Hey, let me stop. I can't stop recording.